which is stable and keeps doing this and then becomes chaotic, and then as you tweak the parameter further, it again becomes periodic and again chaotic? The answer is yes, of course. That's what the logistic map does. There's a whole infinite sequence of bifurcations where this famous logistic map, which we don't have time to discuss, it's a chapter in itself, but this this is xn equal to some parameter mu, xn minus 1 into 1 minus xn minus 1. Now look at what happens very quickly. Again, we are interested in the unit interval. There is interest in what happens in the rest of the real line as well, but we'll focus on the unit interval 0 to 1, 1. So here's x, f of x. And mu is a real number, a parameter, a constant parameter, taking values between 0 and 4 for a reason which will become clear. Now, what does the fixed points look like? The slope at the origin is mu. Linearize about the origin. This term is only one that dominates. And then it's mu. So the slope should be positive, otherwise the map has a different shape altogether. So if the slope is positive and mu is small, then the map looks like this. As long as mu is less than 1. This slope here is mu, and therefore 0 is a stable fixed point. Then, as mu increases, there comes a stage when mu becomes 1 and greater than 1, then there's another fixed point here. And this fixed point occurs at 1 minus 1 over mu. Starts at 0 and splits off. What's happening is a transcritical bifurcation. There's an exchange of stability bifurcation between the fixed point at 1 minus 1 over mu and 0. At the value mu equal to 1, there's a bifurcation. This fellow becomes stable and that becomes unstable. Slope at the origin becomes greater than 1 in magnitude. Then this is the picture. And this is the famous picture which you see in textbooks. So you plot this bifurcation diagram. Here's mu, and here is x star, or a set of points corresponding to a stable periodic orbit. So from 0 up to 1, this is the stable fixed point. There's another branch coming along, 1 minus 1 over mu coming along, which is unstable. But that fellow becomes stable at 1, and this fellow becomes unstable and remains unstable thereafter. After that. Now you can ask, what's the slope at that point? Well, the slope at this point is easy to compute. F prime at 1 minus 1 over mu is equal to 2 minus mu modulus. Trivial algebra. So as long as mu minus 2 is less than 1 in magnitude, that's a stable fixed point. The moment mu hits 3, that goes away. So at mu equal to 3, this starts becoming unstable. The other guy is already unstable. And then you have a period 2 orbit that becomes stable. So now this guy has become unstable at 1 minus 1 over mu equal to 3. And the first iterate of this map looks like this. And there are 2 points here that become stable. Periodic orbit becomes stable. That goes on for a while till at the next bifurcation, period 4 becomes stable and these 2 guys become unstable. And then period 8, period 16, and so on and so forth. You have this cascade of bifurcation, period doubling bifurcations. This is not a pitchfork bifurcation. Looks like it, but it's not. It's not in continuous time. This guy is a fixed point of a map which is stable. It goes into a period 2 orbit which is stable, and this becomes unstable. So it's more like the one that went into a limit cycle kind of thing. It's called a flip bifurcation.
Why flip? One is stable and other one is unstable.
Pardon me?
Why is name flip? One is stable and other one is unstable.
Both are stable and this is unstable. Yeah, that's the period 2 orbit. So the system is jumping between these 2 guys.
That's a flip.
Yeah, that's the period 2. And as mu increases, it jumps here. These 2.
So it's like a soft bifurcation in the species.
Yeah, if you like. And then it becomes period 8, this is unstable and so on. This happens increasingly rapidly till at a magic value of mu, which is 3.577 dot 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 dot. This is known to some 15 decimal places. It's called mu infinity, or the Feigenbaum point. All the 2 to the n cycles become unstable, all of them, and the system becomes chaotic in the sense that the Lyapunov exponent becomes positive for the first time. Before that, the Lyapunov exponent, if you plot as a function of mu, you plot lambda, then of course whenever there's a fixed point here, it will be simply the slope at that point is log mu, and that's negative, so it's somewhere here. At this bifurcation point, this fixed point becomes unstable, so this guy comes and touches 0. It's trying to become chaotic, but now stable periodic orbit takes over, so he goes back disappointed. And then at the next bifurcation, it comes and again touches 0, but again goes back, etc. What happens at mu equal to 2? At mu equal to 2, this map has a very interesting property. It becomes what's called super stable, because the fixed point is at half at this point, at mu equal to 2. And now what happens is that it's a fixed point, it's stable, it's between 1 and 3. And the slope is log 2 minus mu, log mod 2 minus mu, that's lambda, but mu is 2. So it's log 0, which is minus infinity. Because the slope is 0 at that point, the log of it is minus infinity. Super stable. Things zoom into it very, very rapidly. So this guy goes all the way to minus infinity, comes out again, etc. At mu infinity, it emerges fine. And the attractor at that point is a chaotic attractor. Chaos has just started. It's called the Feigenbaum attractor. But lambda is exactly 0, so it's not a chaotic attractor. However, it's a fractal set. And it's called a strange non-chaotic attractor at that point, precisely at the Feigenbaum point. The moment mu increases a little bit more, mu emerges, system becomes chaotic, but then magic is in store. After that, between this point and 4, at 4 the map becomes onto, and after that there's escape starts. So this is mu equal to 4. Fully developed chaos. This fixed point at 3/4 is unstable, and you have, this is a mu equal to 4 picture. At that stage, at mu equal to 4, the full unit interval becomes chaotic. And it gets conjugate by change of variables to the Bernoulli shift itself.
What is mu in fractal set?
Why? Tomorrow I will talk about the sets, fractal sets, and we will explain what a Cantor set is very quickly, and what the measure of it is. We will do a little bit of these measures. So this is the picture, but in between, from here to 4, enormous complexity occurs in the dynamics, even though the rule is so simple. All periods start appearing, one after the other. 2, 4, 6, 2, 4, 8, 16 are already over. Then the next periodic sequence appears, and the next, and the next. Eventually, this theorem, it says, periodic orbits of every integer period will appear. Every integer period. Whether they are stable or unstable is a different question. Most of them remain unstable, buried inside the chaotic region, but they all appear. Finally, at mu equal to square root of 8 minus 1 or something like that, square root of 8 plus 1, a period 3 window appears. There's a transcritical bifurcation, 3 of them at the same time, and you have a period 3 orbit, stable period 3 orbit emerging, and that's the last one to emerge. And there's a theorem, a rigorous theorem, which says that in such maps, for classes of maps, period 3 will be the last one to appear. And after that, no more periodic orbits appear, because everything else has become unstable. And after period 3, you have fully developed chaos. That's called Sarkovsky's theorem. I originally wanted to do that because there's an elementary proof of this theorem for all such maps, provided a certain derivative condition is satisfied on these maps. It's called the Schwarzian derivative condition, but it's too technical to do. So this is roughly this bifurcation sequence. What I'm going to do instead is not get into this bifurcation sequence, but look more carefully at the Bernoulli map and things which are close to it in terms of being piecewise linear, etc. because my target is to really tell you what's the invariant probability measure, because that's what we want to do. Once this time averaging becomes meaningless due to chaos, we want to find out what's the probability measure, what's the equilibrium, quote unquote, measure for probability density, and what's the analog of the Liouville equation in this case, what about its solution, etc. And we look at the measure in phase space itself, because that's what is close to statistical mechanics, and this is what I will focus on tomorrow.
Some announcements. So I just want to remind you of so I just want to remind you all that there is a banquet today at 7:30. It's on the rooftop of the library block building. So all of you are invited. I request all of you who have not returned borrowed books from the library to return them by today, preferably. There's the envelope here, so those who have not returned your feedback forms can put it in this envelope. Feedback about the school, and you can also return your badges which we have taken, so that we can reuse it next time for some school or work. So you can just leave your badges here after the school.